Okay, this video is about problem 5.39. And we're going to be talking about terminal velocity. Okay, so what is the magnitude of acceleration of a skydiver is who is currently falling at 4/5 of his eventual terminal speed? Okay, well, this is a good problem. It talks about terminal velocity, and terminal velocity is the idea that basically the force of drag is going to slow things down as they're falling, and it's going to limit how fast you can fall. And everything in the atmosphere is going to have a terminal velocity. Okay, well, let's start by writing down all of the forces acting on our parachuter. Okay. And here in the okay, so let's start by writing down all of the forces on our parachuter, and then we're gonna go from there. But first we're gonna write down the the force of drag, basically. And we're gonna represent drag by the variable. We're just going to call it D. That's the force of drag. And D is going to equal, um, that's going to be rho times A times V squared times CD divided by 2. Okay, now let's talk about that real quick. Yes. So the important thing that you need to know is what is the force of drag, okay? We're not going to worry so much about the Reynolds number, but the force of drag um, is an important force, and so we're gonna talk about that. So here on the screen is the force of drag. Force of drag equals 1/2 times the coefficient of drag times rho, the density of the fluid or air that the object is moving through, um, the object's cross-sectional area, and its velocity squared. Okay, that's the force of drag. Now, the coefficient of drag is something that is unique to each object, and it depends on the shape of the object. And it's something that we probably need to look up. Okay. So, for example, here are some typical values of uh, a coefficient of drag. And I see a, uh, for a person that's running, that number is 1.2, okay? And it totally depends on the object, right? So the less aerodynamic an object is, the higher that number is going to be. Commercial airliners, pretty aerodynamic, okay? And so that number is going to be really, really low. Okay. Now drag at high Reynolds numbers, which is where most things are that we're going to be dealing with. Okay. So we consider the cross-sectional area of the thing. Okay. And that's going to give us an area, basically. Okay. A cylinder traveling lengthwise, CD equals 0.80. Okay. Um, a cylinder traveling sideways is 1.1. So it depends on the orientation of how this thing is moving through the air. Okay, so if it's say if it's moving sideways, hey, that's going to be different. It's going to be less aerodynamic. Okay, the PowerPoint has a really good explanation of terminal speed. Okay, basically, when an object starts to fall, the force of gravity pulling it down is going to be exactly counterbalanced by the force of drag. So basically, when you fall out of an airplane, hey, eventually you will hit a certain velocity, and that's determined by how aerodynamic you are. So if you want to fall slower, you can hold your arms out like this. If you want to go faster, then you can basically decrease your area and you are going to fall much faster. Let's do it with a piece of tissue paper. And so we can actually see this in action. Okay, so basically here is my tissue paper and I'm going to let it fall. Hmm. Let's try it one more time. Okay, here we go. I'll try not to let it fall down sideways. Okay, so that falls pretty slowly. Okay, let's try it again up here. So, oh, stop zooming in on my face. We'll try it again slowly here. Okay, so um, that's pretty slow. The area of this is much bigger. Okay, and you can see that. Nice. Let's get back in here. Oh, oh, stop zooming in on my face. Ah, I guess I have to move my face down. Here we go. Oh, oh my gosh. Center stage. No. Aha. Okay, we stop the zooming. Here we go. Here's my piece of tissue paper. It's falling. Okay, that hit terminal velocity, and um, that wasn't bad. But now I'm gonna crumple this up. Okay, so I've got my tissue paper. I'm holding it here, and all right. So that was pretty noticeable. Okay, and yeah. So basically, the only difference in those two situations was the area of the tissue paper has changed dramatically. Okay. So this is a lot different area than when it's wadded up. Okay. So let's take a look at this then. So we have the force of drag here, and we'll say that the coefficient of drag for a parachuter, it gives it to us in the presentation as 1.1. Okay, so that's going to be our coefficient of drag. Now, for a person, okay, how are we going to calculate this area? Okay, so let's say here is me, a guy, and I am going to jump out of the airplane. Okay, and I've got a really complicated surface area, something like this. Okay, so what am I going to do? All right, I'm going to make life easier, and I'm just going to make myself a rectangle. Okay, I'm turning myself into a rectangle, and I'm just gonna calculate this area because I can't, I don't know what it is for like the whole me. All right, but I can do a rectangle. Okay, I can do that. All right, so I'm gonna say, all right, just from shoulder to shoulder, this is probably, we'll say, zero point 0.6 meters. Okay, and remember, I don't really have all the information. I'm just gonna, we're just gonna fill in some things. We're gonna kind of make educated guesses and we're gonna put in those numbers, okay? Because a lot of times in physics, there's a temptation to get stuck on the fact that maybe you don't know all of the exact numbers, okay? And so what are you gonna do? Well, you got to make up something. And I think actually, now that I'm thinking about this is probably zero point 0.5, okay? Because I think realistically, I am 0.8. 8 meters this way. Okay. I mean, it's, I don't know. But you know what? I just realized, what do I have here? Oh, it's a tape measure. Oh, we're just gonna take some measurements here. Okay. So from shoulder to shoulder. Oh, it's about, I get, okay, so it was 0.55 meters. Oh, see, that was close. I mean, are those 5 centimeters gonna matter? I don't think so. Okay. The answer is no. All right, but now I need to get my height in meters. Oh, okay. See, I overestimated. So it was actually, oh, no, I'm not 0.8 meters. Oh my gosh, that would be like a Hobbit. 0.8 meters, yes. I'm Bilbo Wisby. Bilbo Wisby is 0.8. Okay, no, I'm actually 1.8, or actually the tape measure says 1.75 meters. Yeah. Okay, so not point 0.8. That I was like, why is my width so close to my height? That was a little bit off, and I realized, oh, the tape measure says I'm 1.75 meters. We're gonna go with that. Okay. All right. So I've got my area now. Okay, so this is my width, and this is my height. Okay, so to get the area there, I'm just going to do area equals height times width. Okay, I'm going to get a number from that, but I'm just going to leave it as A for now. I don't know what that number is. All right, and then the density of air, we can look up that value. Okay, and yeah, the density of air is, we could say, all right, rho is 1.2 kilograms per cubic meter. Okay. That means basically if you have a cubic meter of air, right, it's gonna weigh 1.2 kilograms. Right? And that's pretty crazy if you think about it. And I didn't realize how much that was true until I started scuba diving. Okay, because guess what? If you have a scuba tank here, a full scuba tank weighs more than than an empty one. Okay, that's because you've got pressurized air inside of here, and that pressurized air actually weighs more than normal air. Right? It's much more dense because you pack it in there, and you can actually tell a big difference, or moderately so, if you have a scuba tank. Okay, all right. So we basically got all of our numbers. The only thing that we don't have, and this is why problems with drag are so tricky, is because the force of drag depends on velocity. Okay? And so until you hit terminal velocity, this this force here is going to be constantly changing. Okay? It's going to be constantly changing. Okay? So let's go ahead and let's calculate this. Okay. Okay. So let's get back to the problem. What is the magnitude of the acceleration of the skydiver who's falling at his 4/5 his eventual speed? Okay, here's the problem. All right, so what is the magnitude of acceleration of a skydiver who's falling at 4/5 of his eventual terminal speed? This is going to be really important that we write down all of the forces in this problem. Okay. So, first of all, we know that the total net force, okay. So, the net force is going to equal the difference between the force of gravity, M times G, and then minus his drag. Okay, these are the only two forces acting on him. Okay, that's it. Now, we can plug this in here and it says his yeah, what does it say? Who is falling at 4/5 of his eventual terminal speed. Okay, so his the speed that he's falling at, okay, which we're going to put in here for D. Okay, so we need to first figure out what is our speed that we're falling at, and we need to have the equation for his terminal speed. Okay, so V terminal speed, let's start with that. We can just write that down. It's 2m times G divided by CD times rho over A. Okay, this is how fast you're going to be going when you reach terminal velocity. Um, and so we're going to substitute that in. Okay, so for the force of drag here, yes, for the force of drag, we're going to write this down. So this will be m times g minus rho times a. Then we're going to have here, this is going to be 4/5 the terminal velocity squared times CD um divided by 2. Okay. So the key for this problem is we have to recognize that in our force of drag here, okay, which is up here, we're going to be substituting in that 4/5 of the terminal velocity. Okay. So now we're going to take this and we are going to plug it into here. Okay. And we're going to substitute everything in now. All right. So this is going to give us, and over here, right, we need to remember that, of course, if you don't know anything else, you can always put F equals ma. And so that's what we're going to do over here. We're just going to say this equals mass times acceleration. Okay. Now we're going to finish substituting everything in here. That's ma. Okay. Over here is m times g minus rho times a. I'm going to get all my constants over here. So that constant's going to go over here, and this then divided by 2. Okay, well, now some things are going to cancel. Okay, well, I've got 4/5 here. Okay, so that's going to be, that is going to be 4 squared is 16. And then down here, 5 squared is 25. Okay, and then I finish substituting in here, and everything in here is in the square, in under a square root symbol. So I'm gonna put that in here. We're gonna put everything in so you can see it. Okay, because there's a lot of stuff going on in this problem. All right, so we have 2 times m times g divided by CD over rho times a. And yes, this is I would say, some pretty intense algebra, but we're writing it all down and it's gonna cancel. Okay, so we got the square here of a square root, so that's just gonna go away. Okay, so down here I'm gonna bring everything down. So m times a equals m times g minus rho a over 2 times CD. Okay, and now I'm gonna bring out my 16/25. I'm gonna move that to the end. Okay, but I've got all these constants here. So I've got 2 m times g divided by CD rho times a. Okay, because the square just cancels my square root symbol, and then I've got 16/25 out here. Okay, well, now all this stuff is going to cancel. A lot of stuff is going to cancel. So CD rho a, that just goes away. The 2 cancels. Okay, so now it's not so bad. Oh, and m's. All the m's cancel. I got an m in this term. I got an m in that term. I'm just going to divide m by everything. Okay, so I'm just canceling stuff now. All right, so what are we left with? Now we have a equals g, right? So our total acceleration is equal to the acceleration caused by gravity minus, okay, and now this is actually turns out pretty cool, okay, 16 25ths times g. Okay, all right. So this actually seems pretty reasonable. There was a lot of algebra. We're going to factor out the g now. So we've got 9.81 times 1 minus 16/25. So see what we end up with here is basically the drag cut down on our acceleration by a certain amount. So it actually seems pretty reasonable. It didn't turn out to be too crazy in the end. So we're gonna throw this in MATLAB. All right. Throw it in there, man. All right, man. We'll throw it in there. 1 minus 16 minus 25. Oh, what? No, that ain't right, man. Hey, okay, we got the multiply sign there. You gotta throw that in MATLAB. They don't like it if you don't do it. Oh, okay. So we ended up with A equals 3.5316 meters per second squared. That's my units from there. And then uh I'm gonna round off all the stuff and I'm gonna go to 3.5. So acceleration equals 3.5 meters per second squared. All right, we're gonna go back and put that in. Okay. No, what are we doing? No, I don't want that. Oh, we don't. Oh, there we go. Okay, I don't want to click on that. 3.5 meters per second squared. Submit. Success. The answer is correct. All right. So what do we do here? Well, go back and review. We started by writing down my equations for force. Okay. We identified all of the forces acting on the skydiver. Okay. That was his weight caused by gravity minus the force of drag. Okay. So and we put in our formula for drag here, and then we added the velocity, which is 4/5 of its terminal velocity, and we used the expression for terminal velocity over here. All right, so what should you do? You should put this on your card. Put this on your card. Also, put this on your card. There almost certainly will be a problem about drag on the exam. All right, thanks for watching. There will be more videos about solving, yes, more videos where I solve problems. Thanks for watching. Like and
Thank you. Like and subscribe down below.
thanks.